Hello and welcome back to a new tutorial here on the Ludwig Fusel channel. In the last videos we have kind of concluded all that memory, variable stuff and kind of settled to a point where we understand everything that we need to understand to talk about finally strings. Well, strings is a topic that we have used all the time but never really understand it. I basically always taken that for granted that they exist and that they do what they shall do, mainly in the printf and scanf function. So basically, well, we use printf for example here. This is a simple CF, we printed IO error. This is a string, we use that string to feed it into printf so that it prints that on the screen, or better to say in the console that is on the screen. Same thing here, also a string inside of the printf. The count, second value needs to be bigger than 0. Also here, a string inside of our code, inside of the printf. Never understand what it does really, it just mirrored out to this console, it happened to do that. Now the string was down here, this was a bit more complicated string here. It uses these %i's to basically output x and y. So it really did what it shall do, but we really never understand what it do. In today's video, we're going to completely explore strings, or as good as possible, and we're also going to write a bit of an own printf using printf, but you're going to see this in a second. Before we really start into town and see how strings work, let me quickly create a new project so that we can start from scratch. So I'm going to add a new project here. I'm going to select the empty project. I'm going to click next. Now I'm going to name this 04_strings, press enter, and boom, we have a new project. Now we need to do our general Visual Studio setup code, and now you're tired of that. We're doing this all the time. However, this is important because as long as you work with Visual Studio, the more you're going to get used to it and always making sure that things work. And when you're doing more complex stuff, yeah, you're probably going to be really happy that we have used it quite a lot and that you know what's important to not screw up. Alright, so first I'm going to click on all files so that we see it as it is on disk. Then I'm going to go back to the properties, make sure that we are on all configuration and all platforms, and now I can go to 03 and start copying the output directory and the intermediate directory so that we have this all nicely sorted out. Hit apply between these copies so that everything gets stored, and down here I want to call it strings. Alright, so let's hit apply and press OK, and we have a ready to go project. To really get the project rolling, we need to do 2 more steps. First of all, we need to set this as a startup project so that it gets automatically started when we hit the 5, and of course we need to add a source file to that project. Gonna select the C++ file here again, call it strings and not CPP, just C, so that we are back on C, what we need. Alright, so now we want to start by including the header step we need. We're going to start by the default ones. stdio.h is the first one that I want. Then I want to have stdint.h and stdlib.h so that we have the default, input output, integers, and also for malloc a few functions. I don't think that we're going to need malloc eventually this video, but in the future I might probably allocate some malloc so that we can see what's going on there. Alright, so now let's do our default main function, and for debugging purposes do a quick printf so we see what's going on. So let's just write hello strings and press F5 and see if we're getting that as an output on the screen. And surely enough we get it as an output, which means that we have set it up everything correctly and we are ready to go and start working with strings. Talking about strings, what is the purpose of a string? Well, we already had one in this project, even though I didn't explain anything. This hello strings is a string. So what is a string by just taking a look at this hello strings? Well, it is a sequence of characters, so alphabetic characters that we humans understand to read something, for example. In this case, to print hello strings, that is something that we can interpret. Well, I mean, application that just prints hello strings is maybe useful, maybe not, but it at least interacts with the user and it has something that we can recognize. It is text that we know. Well, let's start by observing step by step what that string is. I'm quickly going to seal it out of the printf, but going to put it back here so that it compiles, an empty string in here. And what I'm going to quickly do is I'm just going to paste the string instead of our source code. And fun fact, if I try to compile and run this, this actually works. Of course, only if you have the semicolon here. If you have the semicolon, fun fact, this works. This is a valid C and also in C++, a valid expression. However, the expression is really useless. It would be this as valid as doing something like that. Write the string it's in value, the 5 is in value. It's both not really doing something that we want. Well, it's just a floating number or a floating value, which is like super unuseful and not something that we want to do, of course. So what we basically need to do is we need to store that string in a variable. And how can we find out what type this string is? Well, we could hover over this to try and see something, but that's going to be quite cryptic and not really understandable yet, but we are getting to that. What we are going to do is the most easy thing. We're going to see what printf accepts and then work our way from that to the variable that we want to do. Alright, so I'm going to right click printf and going to select peak definition. This is going to open up this little window and shows us the implementation, or the better to say the the declaration of printf, and shows us how that function really works. Actually, if you scroll down a bit, the implementation is also there. But what we really care about are these lines, because this is kind of like the function definition of printf. Alright, that definition is quite noisy. There are many things around that. So, for example, here's this check return opt. This check return opt is a macro. This is a special magic value that is just used by the compiler to generate yourself warnings or errors, or the green underlines that we had, for example, which were basically telling us that we had something wrong in that printf. All these stuff is coming from these little helper macros. For example, here we are using the macro check return optional, or OPT. Basically what this means is that it shall check for the return value and it is optional. So basically this tells us that the return value of printf, or not us but the compiler, tells the compiler that the return value of printf is optional. So in case you don't use that return value, the compiler is not going to yell at you. If that would be required, and don't know what the actual format is, if there is a check return required, we could try this actually out. Check return impl optional and what, I don't know. We really don't care what that is doing. This is like something that is like given by Microsoft, and we really don't really care about what's going on there. We just understand this and see, alright, this is just something for the compiler that is not really interesting for us, so we can just think that as is this would not be there. There's also the crt scdio inline. This is also a little helper macro. If I hover over that, you can see that this might resolve to something else. It basically tells you to what this is expanding. Currently this expands to underscore inline. This underscore inline means that the implementation of that function is inline, so it's basically following after the definition, which if you scroll a bit down, you can see, yeah, the implementation is following. This is basically just a hint also for the compiler to prevent some errors when this header is included multiple times. So it's just a little safeguard for the compiler so that it is robust. But also that's something that we don't really care about yet. Next thing we're going to care about is that integer. That integer is for the return value. So we know, okay, printf returns an integer. Did we use that integer? Well, we did not. And so we can basically skip over that and see that's fine. The next thing, underscore crt decal. This is the so-called calling convention. How that shall be kind of like compiled, that function. How that function shall be compiled and called. This is also something that we don't really care about. This has something to do with how the layout is in machine code, and this like depends on which compiler you use, which operating system you use, and you can custom tailor this so that it's basically using that what you expect or want, which you can do for optimization or to make your code compatible with existing function or existing assembler code. But that's really nothing that is interesting for us at all. So all of the things that we saw there, nice to have, nice that they're in here, but for our case, for just detecting the input format of the format, not really useful. So now let's work ourselves into that function. Printf, that's the function how it's called, and now here in the brackets we have the arguments. Let's start at the first argument, which is also the one that we're interested in. The second argument, which are these 3 dots. This is actually a variadic argument, meaning as many arguments as you want. However, this video is not about variadic functions and just about the format of that format string, the first parameter, so we're not gonna care about this as well. So this is the argument that we really care about. The underscore in underscore z underscore printf underscore format underscore string underscore char const pointer char underscore format. Well, quite a long line, but again, we can stripe many things away. First of all, in Z. However, wherever the Z is, probably the Z stands for string, because Z is, for example, also in Java, sometimes referred to as a string, and some other implementations refer to that as string. However, I don't care about this. This basically indicates this is an input argument. This again, same than this check return opt, just for the compiler to basically see, all right, this is an input. And if this is like deferred as an input, it basically does additional validation and checks that your format pointer that you are entering, I'm going to get to this, it's a pointer there, but we're going to get to that, what is this exactly in a second. However, it's kind of like validating that this pointer is already set, and as you know, pointers, they might be used so that the function actually sets the data. So it could be a pointer to some empty data or something like that, and this basically just makes sure that it is an input pointer, it's not null, and it's everything so that the compiler can warn if it sees an issue there. Second thing is that one, printf format string. This printf format string is also for the compiler, especially for these green underlines that we had when we had the wrong format, is the format string. So for example, if we would go to our simple C app and maybe scroll a bit down and change that one from I to maybe C, which would be wrong. C is wrong, and I hope that it's going to detect this. No, it's not detecting this because it could work as C, but S is totally wrong. S should result in these green underlines. And basically, these green underlines are coming because that format string is wrong that we now entered. The thing is, this format string is not something that is like defined in C++. This is the only thing that it can underline this green is because that macro is in here. Printf format string. This is giving the compiler the hint that this is a format string, a C format string, and this kind of like triggers additional checks and validates the format that we had previously. Also that, just a little helper for the compiler. So basically what we are left with is just this expression. Char const pointer const underscore format. Alright, underscore format is quite easy. That's the name of that variable. It's probably used somewhere down here. Yeah, here, 2 times format. Now, what is everything that we have around here? Well, let's deconstruct this according to the last video that I've made. So I told you that everything is on the left here. That is the type. That's the actual type we are referring to. And so on the right is just the modifier for that pointer. So this const here on the right of that pointer basically just means that printf itself cannot modify the underscore format variable itself. Well, it is just a copy, but the function cannot really modify it. It's not allowed to modify it. So we really, to just care about what a string is, just need to take a look at these 2 things. So we are already down at 2. Now this is a char const pointer. We in the last video always used the format const char pointer, or last video const int32t pointer and not int32t const pointer. Really, it's the same. You can change that constant type as you want. So char const pointer and const char pointer in this case would be the same. The thing is that I like to have the const first because that const is not affecting the pointer. If you're writing it like that, it kind of like has the... It's kind of like luring you into the state that you think, all right, it's a char, but the pointer is constant. No, it is a const char pointer. It is a const char that is like the type that we are trying to point to. This is why I like to call them const char pointer. And most of the time, you're going to see const char pointer. However, the standard library here in Microsoft does it the other way around. So really what you need to do is you need to virtually flip these. I can edit this here. I cannot save it. If I would try to save, it's going to bring up that save dialog and throw me back to that file if I try to escape there out. But just for readabilities, I can show this to you. So const char pointer is kind of like the type that we really have here. Okay, so const is quite simple. The const here on the left basically means that that type here is constant. So everything where this pointer is pointing to is constant. So basically we have a pointer to a constant char, which basically means that this is a char and we cannot modify that char. All right, good. So basically what we have then as an argument is a pointer to a constant char. A constant char, multiple constant char, an array, we don't really know. Is it a single char pointer or is it a array pointer? I'm gonna say it's an array. I know it, but my observation here is it is a char, and if we just have one parameter and one parameter that already exists, we would really think that if it would just be a single char, we don't know what a char is yet, I don't think that we have talked about this, but if it would be a single char, then it wouldn't make any sense to have this as a pointer. Right, so because it's a single type, it's not an array, it's not a a struct. It is a basic char. We can get to that, what is a basic char is. And basically by just having a basic char, really an array makes more sense. But we're going to get to this in another way as well. All right, so really what this is a const char pointer, what we are trying to insert into that printf. Let me quickly close this up. We're just going to try to save this, but we don't. So yeah, that's where we go. So basically it's just a const char pointer. I'm just going to call the variable string here and assign it to that variable. And as you can see, surely that works, because this is the same thing that was given to printf. And if I would now also modify this around and also give this as a parameter to printf, you can see no errors here. And if I put pref as F5, we should have the old behavior back. Yeah, we have the old behavior back. We are printing hello strings. All right, so now let's dive into and take a look at what this all is. First of all, let's make a breakpoint before we printf and take a look at the debugger. So I'm going to go to my locals here, and as you can see, the string has been recognized. You can see we have the variable name string, we have a value in here, which is a pointer value. That's correct, it's an address, and the type here is detected as const char, and as you can see, it is also recognizing this, and instead of these quotation marks, double quotation marks, it is going to show us a preview of that string, and it tells us hello string. You can also press this button here on the right, especially if you're having long strings, that view button. If you click on this, it's going to bring up this text visualizer, which is showing you the whole string. If it gets bigger, you can scroll around, you can wrap it automatically. If it's getting too wide, you can move this around. You can really take a look at this and really abuse it. This text viewer, just for your information, has multiple modes. By default, this is on text visualizer. It can also detect XML data, JSON data, and HTML data. So if I would kind of like change this, it tries to parse this as an XML. XML is a special format, which we might get to in the future as well in a video. Maybe we're going to talk about serialization and C++ stuff. And XML is one way of kind of like storing key and value pairs as a special format in a text, in a string. And basically, this would just allow you to browse these. Same here with JSON and HTML. If you're processing like an HTML, you can basically see it here. And actually, HTML works without any text in there. HTML also works if you're just having a file where some text is in here. So you can actually see this now is a bit more markable and looks a bit different. This is actually now a web page which it tries to emulate there. So if I would like try to, maybe we could try this. So let's maybe say H1 style. Yeah, I now need to abuse something that you don't know yet. Color red. If I would do something like that, this is just some basic HTML. And would try this out again. Let's try to rerun this. Don't know if my HTML is a bit roasted, but yeah, if I would try to visualize that, we are getting a red hello strings here because it's kind of like detecting this as HTML and parsing as HTML. However, this is now already including some stuff that I haven't talked to you through, so I'm going to remove it very quickly so that you don't get confused. And basically, this is just it's just a nice little tool, and that's something you need to be aware of, that it is there, because if you're coming to XML, HTML, or JSON within C++, it's good to know that this is there, that you don't need to always have like a separate browser and need to copy over and check that everything works. These are there, you can view them, you can press that drop down, and you can make sure that everything is good. Okay, so enough of that. So as you can see, it kind of like detects that string. Okay, so now let's dive a bit into that const char pointer. So as I told you, we have like two options what that const char pointer can be. So it can either be a pointer to a single char, or it could be an array of multiple chars. What would happen if it would be a single pointer to a single char? Well, maybe the char is a ID. Maybe the char is an ID that represents the string, and the compiler kind of like tries to find out where the string is because of that ID. Well, let's test it out. Does that work if we are going to watch and just try to access the first element of that string? So I'm just going to type the name, string, do 2 brackets there, and enter the index 0 to access the first element. And when you're now taking a look at this, you can see that we are now back from const char pointer to const char. So now we are actually at a const char. And as you can see, the string is now no longer readable. We just get an H. And really oddly, this H is the first character in our string. And this should already put you on the right track, because if you are having the index 0, which is like the first index in an array, and you are getting the first character that you have in your string, the observation that this is an array is really, really high. So if I would go to true, I would now expect to get an E, and surely enough I get an E. By the way, if you have noticed, left to that E, you can actually see that we always get a number. We're gonna get to what these numbers mean in a second. Could continue this on, could maybe go to the 5, and 5 would be like 1, 0, 1, 2, 3, 4, 5. Is the space in between here, and as you can see, surely enough, we have empty single quotes, so it indicates a space. Let's maybe go a bit further to the exclamation mark maybe. 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13, that's the index. If I write it in here, we get the exclamation mark surely. What would happen if we go further? So 14, do we get something? Yeah, we actually get something. We get a 0, which is being displayed as a \0. And we could go further, but we are gonna get another 0 here, and if we go far further, we still have, mean to be having zeros here, but if we might, the thing is, we are like, at some point we might hit something different. Yeah, at 80 we hit something different that we can't interpret. It's a question mark. So as I have as an observation here is every index from 0 to, as long as that string was valid, then we got it a few zeros, and after that we have had some invalid data that we can't parse. So observation out of that is, well, we seem to have an array where each readable character for the human is an index in that array. So by providing that string here, we really get an array. Is it that? Yeah, it's not as simple as that, but we're going to get to it. It's not a real array, it's kind of like a pointer to a string, but a string is actually an array. A string, and this is the getaway from that debugging session here, the string is an array of chars, and a char is, as we could now observe, a single character in a string, or a single human readable character. HELLO space strings exclamation mark, whatever. Every of these characters was like one char in that array. So now what is a char? Let's try and find out what a char is. We were able to have one character in here, so let's try to put that H into a char, and let's just call this C. Char C, and let's try to put that H in. Let's press the rerun button and see what we get if we're doing this like that. Well, let's go to locals and take a look at this. Our C is empty. Why is our C empty and not containing an H? Well, I don't know. One important observation, if you're rerunning this might give you something else. Gonna try to rerun this a few times, but we don't really get a change here. We might get a change, but probably because we are in debug, we don't get a change. However, what we are doing here is wrong. As I told you, a string, if we have it in quotation marks, is a pointer to a char array. And what we've done here is creating a string as well. This is a string, however, there's just one char in there. And even if we just have one char, it is still an array, it is still a pointer that we get. So this doesn't really work. If we just want to have a single char, we need to manually do this with the single quotation marks. So if I do this with single quotation marks and rerun this, we surely get our H in here. So now the C is a H with the magic value of 72, these values that we always had on the left. Now I want to talk about these values. Actually, if you hover over that H here as well, let me first stop this. Even if you're not in debugging, if you hover over this H, you can see that this H actually gets converted to an integer of the value 72. So what's really happening is that this char is actually an integer. And we talked about integers previously. We always use them like uint, 32, T, for example, and stuff like that. And actually, the char is also used as an integer. So an int 8t, an 8-bit integer, if I would take a look at this by right-clicking and saying peak definition, we can actually see that an 8-bit integer is a char, a signed char. A signed char basically means just a char which can be negative, which it can be by default. If you're just having a char, it always can be negative. However, this is just to be a bit more explicit. It's explicitly defining signed because int at always means to be signed. There are a few, it could be that a char might not be signed, so this is like explicitly defining that. But in our cases that we do, it's always gonna be signed. So basically what the int at is, if we just hover over that without picking, it is a type-left char. So int at is basically a char, or on the other way around, a char is an 8-bit integer. So basically what a char is an integer. Now you're a bit confused because we actually assigned a human readable character. How can that be that a human readable character is an integer? Well, if we talk about computers, computers are mathematical units. They are built by electrical engineers and mathematicians, which later turned out to get into a whole new division of engineering, software engineering, information technology. These all went out of that electrical engineering and math, because the initial people who built computers were electrical engineer and mathematicians. So basically what they have done, they have built computers to crunch numbers. What the computer can do is it can always only deal with numbers. Actually, it's even trivial. A computer just can deal with 0 or 1, electrical on-off. That's the only thing the computer can do. However, what we have done is we have assembled many of these on-offs together, so many of these bits together, to form integers, like 8-bit integers, 16-bit integers, 32-bit integers, 64-bit integer, and today's even 128-bit integers, or even bigger integers. So basically the idea was here that mathematicians and electrical engineers have put in together physics, electrical engineering, physics together into a math processing unit. And the math processing unit can basically use bits, so single on-off states, to do math. And the math that it does is really just limited to integer and floating point math. That's like what a computer can do. Integer math, floating point math. Not even variables. Like, this is not even a concept. The variable turns out to be an address on the stack if it's compiled. And function as well. Turns out to be that name turns out to be a address. String, the pointer, is also an address. It's everything in address. Everything on the computer that is being computed by the CPU is going to be turned to a number. And so that we as stupid programmers can actually handle that better, we have the compilers that basically take our textual representation that we write in C, C++, later on also like Python's, all these scripting languages. At some point, they are all going to be turned into math. Integer math, floating point math, anything like that. Everything is going to be math. And, well, math doesn't know English. Math doesn't know English, German, nothing at all. The math doesn't speak a language. The numbers doesn't speak languages. I mean, yeah, you can annotate stuff in math if you're doing math on paper. But in general, math does not handle languages. Just handles numbers and special statements. But yeah, you get my point. So really what the issue is that we are faced when we are trying to put these human readable characters that are just there for the human, right? If we would just write a program that does computations like a database, we don't need these strings. We don't need strings at all. We can store everything with numbers. We don't really care what numbers are coming in. We don't care how the numbers come out. We are just crunching numbers and storing them somewhere. So basically, strings are just a concept for humans. And well, they are a quite clever concept and make many things, especially for us humans, way more easier, but they also come with a problem. The thing is, as I told you, strings, easy for the human, but the computer doesn't understand them. So what we need to do is we need to find a way to represent strings, or actually even characters, single characters, for the computers in numbers. So basically the idea is a string is an array of characters, and the character needs to be defined as an integer so that the computer can understand it. And that's what's happening here. The single quotation marks are nothing more than a lookup into a table. A table that has all of the characters that the human alphabet knows, like the A, B, C, D, E, F, G. All these characters are basically stored somewhere in a table. So basically compiler has a table and basically knows which character stands for which number. And basically what it does is it converts the character to a number. For example here, age 72. It's really just stored as a number for ourselves so that we can represent that and we can take a look at this. It is converting this to like the characters. As you can see, we can write it here as characters, we can write it as strings. If you're going into a debug session, the debugger is smart enough to also display us that as a string, display us the character as a character. Here we could even go in and modify that character, make this to an E. Could also go in and write actual values there to make the characters work. So really what's going on there is that the compiler and the debugger basically says, all right, this is a character, an 8-bit integer. It's probably going to be a string because 8-bit integers, if you're not on the 8-bit systems, are on these days just used, or most of the time just used for displaying characters and strings. And This is because, well, it's the smallest type, and most of the time you need more than the value range of a 8-bit number. And what the compiler then does, and all of our tools does, is they all interpret them as strings. And this is all a construct that has been built for us, the humans, so that we can interact with humans with the application, that we can write them as humans, the application, that we can debug them as humans and see this all nicely as strings. But under the hood, these are just numbers. And if we would take a look at this again, let's start over so that we don't have these modified values in here. If I would take a look at these address, this pointer, and go to my memory view, if you don't have it open, can go to debug, Windows, memory 1, and that's going to open up that memory window. We can paste in the address here, and we can actually take a look at this, and actually can see the address. It starts here, and what it is basically a range of numbers. These are now hexadecimal. Here they were decimal. Here on the right they are hexadecimal. I could actually switch this around. You can right click this and say hexadecimal display so that you can see 0x48. And if I take a look at this here on the right, this is also 48 because hello strings begins with an H. So the first string is an H, and an H is 0x48, as you can see here in the C. So also right on the memory on the full string begins with 48. If I take a look at this, you can see many numbers. Each of these number blocks, every 2 numbers is a new character. And at some point we are finding that 0 that we could also observe previously when we tried to understand this and use the watch 1 to basically go through the array on debug mode. So as you can see, we have a range of numbers that are followed by a few zeros. And on the right here, actually, you can again see a representation hello strings and a few spaces. And if you are taking a look a bit down lower, you can actually see that there are actually more strings stored somewhere in our application. We never specified that string. We never specified the string stack around the variable was corrupted. Well, we got that error already previously in a video. So we got the stack corruption error. So basically, as you can see, this error is actually stored somehow and somewhere in our application. So our application is actually aware of that error as a string as well, so that this can kind of like be done. And if you scroll a bit around, you're gonna find a few more error messages that are all like coming from the runtime checks and Visual Studio libraries, Microsoft standard libraries that are basically basically showing you what's going on. For example, here's an unknown file name, unknown module name, runtime check failure, stack corrupted near unknown variable, stack around, whatever. We have a hell of a lot of messages in here. This is actually a special thing. I'm going to come to that later on. Basically, all these strings that are used in the application are put together in one single spot of memory, which happens to be that one here currently. So really what's going on is that we have a range of numbers. How are these numbers defined? The numbers for the characters are not random. They are actually well defined. And the most popular one is the ASCII code. The ASCII code is a special code that basically defines each character and pairs it with a number. So if we are opening up a ASCII chart here on the internet, you can actually see what this looks like. As you can see on the left here, we have some decimals that are going up until 127, so from 0 to 127, which basically means that we are just using on ASCII code the positive values of the int 8t, so we're just basically using 7 bits out of the 8 bits, so the rest on this kind of like spare. And if you take a look at this, every of these numbers from 0 to 128 is assigned to one character. Well, character is a bit misleading here. It's not all visible characters. As you can see, every character here on the left having special names like null, start of heading, start of text, end of transmission, inquiry, bam, escape, file separator, unit separator, kind of like interesting values. These are so-called control characters. Control characters were used especially on very old systems. You need to know that ASCII is quite old, and ASCII was very extensively used earlier for like many years. I don't know how many years exactly is that. It's still used today, but like the full glory of ASCII is actually a long time ago. And basically what these control characters they were basically control characters to interact with systems. So for example, ASCII characters were sent through a server. So if you're communicating with a server over a serial interface or SSH is a bit more advanced, but basically what they are doing is they are sending around these ASCII characters or any kind of like character set, and to basically also send around, like if you're pressing the delete button or the enter button and stuff like that, it's basically also having these control characters that basically indicate special conditions like pressing the delete button, pressing the enter key, pressing the tabulator key, control key, alt key, all of the things, so that you kind of like send them over as well and interpret them as well. Now, if you're taking a look on the next column here, you can actually see that we are getting a bit more concrete and have something that we can understand. So the first thing at location 32 is space. Space looks like a controlled car on this chart here. However, it is not. It's basically just how they are writing it, because a space, you wouldn't see a space here because they are not having like the single quotation marks like Visual Studio had them. So really, space means the actual space bar button. So having a blanket there between. You can also see after that space we are getting a bit more reasonable characters, exclamation mark, quotation marks, hashtag, $, and then a few other chars followed by 0 to 9, followed by a few chars. Then we got on the next column the @ we got A to Z in alphabetical order starting at 65, a few more brackets, slashes and stuff like that. Then at 97 we start with a small a up to 122 with a small z, a few more control chars follow, a few more special chars followed by a delete. Delete is also a special control char that might be used for deleting something. It's not backspace. I think delete is like the delete key on the keyboard, I think, as far as I know. Should be. So this is basically how everything is encoded, and we can quickly verify this. For example, our age has a value of 72. We had this a few times, the 72. Also the space, 32. We also had this previously. So these values are actually the same values that we observed earlier on in our coding adventure here. So basically, this is the mapping table that is happening there. Well, not kind of like the truth. Actually, what we are using when we are programming on Windows, we are using Windows 1252, often referred to Windows 1252. And Windows 1252 is basically dependent on the ASCII set. So actually, it's completely the same than ASCII. You can see exclamation mark, quotation mark, hashtag, $, %, starting with 0 to 9, A to Z in big, A to Z in small, and at the end the delete key. However, this is like completely ASCII. From there to there, it's completely ASCII. The only thing Windows does, it is adding a few more commonly used characters after that. So as you can see, we have a few more, like the euro sign, functions, like the German quotation marks. Also, like here, French and another German quotation marks. These are, I think, also French quotation marks. Not quite sure are they from which language they are, but these are also quotation marks. I think these are French ones. I don't know. Is that a French one? Maybe if I hover over that. Quotation marks. Yeah, these are also. Like they are adding a few versions of quotation marks, a few mathematical things like power of 2, power of 3, plus minus, degree, copyright symbols, paragraph symbols, pound sign for pound. $sign was already up there, I think, somewhere. Yeah, so we have like euro and pound in here. We have promille sign here. Per mil, it's called per mil, okay. So then we have a few special language things like the German, and Ü, and the German scharfes S, SZ, and French characters like the apostrophe, the AQ. No, is it the Chinese? I think it's also French, yeah. French stuff and accent de... I don't know, these are not the French terms. These are not the French terms. However, these are also used in French. I had this language here. Or 1/4, 2/4, 3/4. Like, it's adding a few more extensions. The Windows code page is adding a few extensions, and they might be usable or might not. If you are using C, be aware, probably only the ASCII characters work. Even through Visual Studio tricks you into thinking they work. You can type them, and they are going to work. We can read and write them and use them. However, if I get past, can see that they are not really used. They are not mapped correctly. We are kind of using Windows stuff there with that power to 3. However, they are not correctly mapped. These are not correctly mapped. They are not guaranteed to work. These are not guaranteed. So if you are working with C and normal strings, limit yourself to the ASCII table. Even through like Windows is encoding them correctly. If I would now put them back here like that, if I would put them back here and again go to the memory view very quickly, copy that over, you can see if we are taking a look at this on the right here, you can see that actually A, Ö, and scharfes S is actually shown there. So the characters are properly stored in Windows. This is because this is the Windows native format. This is the Windows native encoding, how Windows lays out the memory editor. The memory itself, this is all the same. On Windows they work, but not on C, because on C they are only defined as ASCII characters. So only ASCII is on C available as const char. This is why printf is not really handling them well. They are kind of like handling it, and we are not really getting defined behavior if you are using chars out of that Windows range. However, they are available, and if you are going to C++ and use a bit more advanced strings, we can also use them. But for now, just if you are using const char pointer, just use these ones. Alright, so now we basically know how this works. Now I want to quickly talk about these control characters. So the control characters basically define several states of the text that you are doing. And most of them are not relevant to us. There are actually four control characters that we need to know. What are the control characters that we need to know? We need to know null. Null stands end of string. We have like this end of text. However, end of text is often used as a valid character to be sent over an interface, for example. This is why we cannot use like end of text or end of transmission to indicate the end of a string. String is always ended. Every string that you have in C and C++ is always going to be ended or terminated with a null char. So a char with the value null or the escape sequence null to basically indicate that the string has come to an end. And this is what we observed there as well. So basically at the end of the string, I can also like type in string here to get it. So you can see the last one here is a 0, and this 0 is actually null terminator and tells that we have end of the string. We have reached the end of the string. Why do we need a null terminator? Well, because printf just takes a const char pointer. A const char pointer is just a pointer to the first character. The first character, however, is the age. It's not aware of where that string ends. So basically what printf is doing, it is basically taking characters as long as it can take characters until it hits the first 0. And as soon as it hits the first 0, it basically knows, all right, this is the null terminator. I need to stop reading because everything that is beyond that null can be invalid memory. Can be memory that is not being defined on a proper state, can be memory that's not accessible and results in an access violation. And everything after that null terminator is not to be accessed by any function takes a string. Every function that takes a normal C string should always only ever access the string up to that 0 terminator. And that 0 terminator, as you can see, is by default inserted if we are doing a string like that. If we have a single char, we have just one char. However, if we are doing a real string like that, the 0 terminator is generated for us on the fly. This is not for granted. If you are writing poor assembler, you would always need to specify the null terminator, and the null terminator is specified by writing /0. 0 alone would not be enough, because 0 basically means, well, 0, of course, and 0 means 0, and 0 is a valid character that we can print. So if we basically want to indicate that null, that end of line, that 0, we need to put a special escape character on top of that. So an escape character is basically a character that tells the compiler that the following character or the following characters shall not be used as a raw character for the string. It shall be used as a control sequence. In this case, /0 means insert that null terminator. What you can also do is you can specify X. If you specify X, you basically tell it that you are doing a hexadecimal input. Hexadecimal input, in this case 00, also means the null terminator. So if we would see this, hex 0 is null. For example, if I want to hit that bell, I could write 0x07. This would be the bell character, which should, I don't know if this still works, has a nice effect. Little dim, did you hear it? It looks a bit ugly because it hasn't cleared the console. Let's do this again. You kind of like hear that Windows made this dim sound, and the dim sound is actually the bell. That's 0x07, which is the control sequence for bell, basically made our computer do a bell sound. The bell. So actually you can like directly index these hexadecimal characters. I could also like try to find a character. So what is a character, for example? We can use, for example, a plus sign, it's 2b. So if I would do like 2b on this escape character, on this escape sequence, it would print a plus here. So really what I can do is I can escape that string and say, hey, put that raw value on there. Or what I can always say is, hey, I want to have a 0 in here. Or what I can also say is, hey, I want to have a quotation mark in here. Because a quotation mark is a reserved character. And if I put in a quotation mark here, basically the compiler thinks that the string is at an end. However, if I do this escape sequence, it's basically telling like, hey, ignore that quotation mark as a control sequence. This is an escape character. The backslash escapes that normal string, says, okay, now there's a special character coming, and if you're putting a quotation mark in there, it's basically telling us, hey, that quotation mark shall be printed, and surely enough, quotation mark is printed. This also works for a backslash. If you want to write a normal backslash, it doesn't work because the backslash itself is a escape sequence. So if you're doing like a double backslash, it's going to write you a normal backslash in there. And this really works for many things. For example, there's a N. That N stands for new line, or to speak in ASCII code, line feed. So if I would do a backslash N here and then say hello strings again, if I would do this with that backslash N in between, you can see it is going to split this into 2 lines. So the backslash N is kind of like a so-called line feed. If we would take a look at this chart here again, you can see that line feed is here, defined as 10 or hexadecimal A, which basically is our backslash. So if I would do this like with an A here, it would have the same effect here. Going in that console here again, having it as a nicely separated. However, like doing always these hexadecimal displays is not really nice. This is why we can like do something like that, or that, for example. And what we can also do is like this backslash t. This backslash t is a tabulator. The tabulator is basically putting a space in between. This is a bit bad here. Let's maybe do 2 tabulators that you're really seeing what's going on here. So 2 tabs here, and you can see that they are way apart. They're more apart than 2 like empty spaces. Tabs are kind of like a bit responsive. If I would like add something on here, 1 character, the width between them, oh no, I make it a bit closer. It's not going to change. So yeah, that's how this works. So these are basically special characters in between that you can use to control the flow of your string. Now, one thing that we had last video, we had this pre D8, for example. These they are not included here. They would be in int types.h. We had this pre-D8, and this pre-D8 is basically just the text. So this pre-D8 in this case is an HHD, so pre-8 is basically just HHD. And what you can basically do is you can put these strings together how you like. This is valid. And if I would run this, you can see basically that it's like appending them all together. This is very, very useful, especially later on if you are trying to concatenate several strings together in a special way. It doesn't work on the runtime way, it just works on the compile time way to concatenate strings together, and it's really nice. So for example, what you could have later on is I'm gonna throw you something that you haven't seen, like this XD here, and this XD could be hey lol, and what you could basically then do and say, alright, I wanna XD I want to XD a hello world out there. And if I want to XD a hello world, you can see that you get this hey lol hello world, which is basically making it a bit easier to display something. Or what you could do is also use this as like prefixes for strings and stuff like that to flag them. For example, if you're having an error, you could like prefix this error. You kind of like see a new mechanic here that I'm going to explain to you in more details in the future. But I can like say, all right, this is an error hello world, and you can, of course, surely get this error hello world. It's basically just a helper that you can put in strings together in a compile time way. Alright, so this is basically how these strings work. A string is just an array of characters, and each character is just a magic value that makes no sense for the computer, just any integer value. The computer just deals it as an integer. However, all the libraries that are built around C and also C++ and around what we understand, all of our tools, they are all like coded that way that these are actually strings and characters that we can read. It's just somebody has come up with that concept and everybody uses that from there on. And that's basically how these strings work. There is one more thing that I want to tell you and want to show you. I know that video is quite long already, but strings is an important topic because they are not hard to understand if you understand arrays, if you understand pointers, and if you are getting this right. So what can we do with strings as well? Well, currently you can see that we had the string here as a const char pointer, because this one is actually stored in a special location. Where is that stored? Well, this is actually stored in our ASCII. So what we are going to do now is something that you're probably not never going to do in a real use case, but I'm going to do this to you to show it to you. If I open up my directory where I have my project, go into my build directory, in my binary directory, and in my debug directory, I'm going to find the strings.exe file. And what I'm going to do is I'm going to open this up with Notepad++. I installed it, by the way, now, finally. And now, of course, it's going to try to fool you into something where I already looked that up. Let's go quickly back. Now, come on. Quickly go back to the beginning of that, and this is basically how our exe looks like. It's not really understandable. However, what I can do is I can Control F for my hello world, and actually we're going to find that hello world. Actually, you can see that error is actually still next to it because we hadn't recompiled it after I removed that error. So actually, as you can see in our exe file somewhere we have that string hello world, and if that exe file wouldn't be like validated with a checksum, we could actually go in and change text here, and it would in theory also validate this, but I think it's not possible. We could try this out just out of curiosity. Hello mem, so something like that. I probably think that this doesn't work, but I'm not quite sure if that might work. String exe. Yeah, this app can't run on your PC, basically because we have corrupted that exe by changing some code. If I would fix that, it would again work. This is just because it basically there are some checks around that exe file that disallow you modifying that value actually. One thing that I want to show you additionally, if I can find my cursor, but I never can do it because Notepad++ is so bright that you really can't see your cursor. There it is somewhere. Come on, where is it? There. Alright, so if we are actually down here and we scroll a bit through there, we are actually going to find some more strings that are familiar. Well, as we experienced around and tested around the memory view, you actually saw that we had other strings around the hello string text. For example, that stack around the variable was corrupted. We already saw that in the memory view. Same here, the variable is being used without being initialized. The value of ESP was not properly saved across a function call. So all of these like texts that we saw earlier on that memory view are there as well. And actually, as you can see, this line is basically one-to-one loaded into the application. So if the exe starts up, Windows is basically loading this line 90 out of our exe file. It's basically copying that into RAM, and then you can basically create a pointer to that location and start reading that string from there. So actually what Windows does is it actually loads this one-to-one from the exe to that memory that we use during runtime of our application. Same happens actually for the static variables. The static variables are also somewhere stored inside of this file here, and at runtime when we start, the static variables are copied to the memory, and then we access it and modify it. However, since these strings are not really meant to be edited, these strings are not static. If we are like declaring a static string, yeah, that might be true. If I want to have a string that I want to edit, I would probably do something like static char pointer lol. If I do this like that, I can of course do this, and now I would have an editable string. I'm not quite sure if this actually works on C++. We might be worth a try, but it's really not something that you do. You don't really have static strings on your system. Most of the time you're going to have these strings, and if they need to be like dynamic, you're gonna have like formats in these strings, and then they are at runtime like filled in these formats. Or you're gonna use, when we are at C++, you're gonna use string streams, but that's a whole different story. So basically what you are doing here is you are never going to change this. This is why strings are always going to be const char pointers. C is quite graceful. C actually allows you to not have this as a const char pointer. However, I'm going to tell you always put this as a const char pointer. Makes your life easier if you always have this as a const char pointer. It's not modifiable. Could even go further and make this const as well here, but that's really not the point here. So actually this string is set in stone. We cannot change it. We cannot change it. It is there as it is. But what happens if we want to modify a string? Well, in the next video we're going to learn a few functions where we can actually copy strings around and make this a bit more easier. But for now I am just going to create a string on the stack. How do we do it? Well, we just define a modifiable string, but now no longer a pointer. Now we're going to do an array. So let's just call the string edit. We're just going to create an array of, let's say, 265 characters and call it edit. And now we can basically edit the string to our purpose. How do we need to do this? Well, we need to do this manually with the array access operator. I'm just going to write in lol here because this is going to be easier for me to type down. Again, we're going to talk about a few functions that make our life easier in this case in the next video, but just for now, we do it like that. So now if you would fill in this lol, you would think that you are fine, but no, you are not. I can prove this to you if we start this. Invalid characters in string. Added is not recognized. Why is that? Well, we forgot our zero terminator. If we are constructing our... Okay, we even made a bigger mistake. We actually had the wrong character here. We need to have these in single quotes, of course. They need to be in single quotes. If we don't have them in single quotes, they will not work. Let's uncomment this quickly and show you that it still doesn't work. Still, if we make this correctly in single quotes, it doesn't work. If we expand this array, we can see that the first three characters are okay, but the rest of the characters are at this question mark, and this question mark basically means invalid. It's invalid, it doesn't work. So we really are doing something wrong. We are missing our null terminator. I told you that everything needs to be null terminated so that we know where we need to end our parsing. And we just need to fill it in like that. If we're now adding the null terminator here, and run this, well, it is going to be, of course, needs to be at the next location, or we're going to overwrite that L. It's going to be lol and detected and recognized correctly on the system. Maybe put this back into normal display so that we see this a bit more better. All right, so this works as well. You can do strings like that as well. You cannot do these strings like that because of the way the memory is loaded out. The memory, that lol here, is now actually stored on the stack. If I could edit this. This is like the stack. It's in a complete different location. You can already tell this because the addresses of these two pointers are quite far apart. Like this is like very low, and this is a very more higher address, and it's apart. So basically here are our strings, and between them there's some bunch of uninitialized memory. There might be code between. I don't know. There's many things. This is probably the code of our application here. This could be the code of our application. No idea if it is the code of the application, but it might, because they are always like often grouped together. So you can basically see there are many bytes between them, and I cannot scroll them because it's really far apart. Go back to edit. There we are. Or we'll go back to string. They are basically stored way apart. They are stored way apart. They are in complete different sections now. The one is on the stack, and the other one is stored inside of the application and is set in stone. It's not really set in stone. You can force this to change. Don't know if Microsoft allows you to do that. I know that C in general should allow it. I don't know if Microsoft has a nuance that doesn't allow you to do that. We're gonna see in a second. No, it is not allowing us to do that because Microsoft does not allow you to change these. However, in sometimes this might work, sometimes it might not work. Microsoft does not allow this. I think that the Microsoft compiler is getting it the right way because it's not meant to be changed. That's because there is a feature called string pooling. String pooling means that same strings are going to be copied into the same location. So if I would do string 2, string 3, and string 4 that are all set to hello world, if I would run this, you can actually see that they all have the same address, right? They all have the same address because they are the same string. We have them 1, 2, 3, 4, 5 times. However, in memory, the string itself is just existing one time. This is an optimization because probably if you are writing a big application, you are going to probably have some strings multiple times in the application. And this is just like reducing the memory consumption and reducing the disk usage by basically pooling all these strings together. So the strings are basically, the text is all right, hello world is already there, so I'm not going to create a new copy. They are all getting the same copy. It's even happening on debug, as you can see, and this is why you should not modify them. And this is like also why C++ is such a nice programming language, C and C++, because they do things like that. And that's really, really nice there. So, nice features, amazing strings, basically just numbers, special numbers in a sequence together, and can deal them however you like. You can deal them with pointers and arrays. Nice thing is, if we do it like that, directly a pointer. So I hope this was understandable and not too long. I mean, it was kind of long, this video. However, there were a few things that I wanted to really cover well. The code that we produced was for very, very short for that long video, but I hope that you really got what we did here. Alright, so thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye!